Hey, Algebra students. In this video, we're going to be talking about a probability topic. We're going to be talking about mutually exclusive events and inclusive events. First of all, we need to define what mutually exclusive events are. Mutually exclusive events are events that cannot occur together on the same trial of an experiment. Over here, I have a table that you should really memorize, okay? This table shows all of the possible outcomes of rolling two dice, two number cubes at the same time. Notice if we roll two six-sided number cubes, we can get numbers as low as 2. And notice the first row, so if I roll a 1 and a 1, I get 2. A 1 and a 2, I get 3. 1 and 3, 4. Notice I start with 2 and I just count up by 1 as I go across the table. So 2, 3, 4, 5, 6, 7. The next row starts with 3 because 1 and 2 is 3. 3, 4, 5, 6, 7, 8. 4, 5, 6, 7, 8, 9. 5, 6, 7, 8, 9, 10, and so on. You can kind of see how the pattern of this table works out until I get up to the highest possible roll, a 12. Now notice that numbers keep getting bigger from top to bottom and from left to right, okay? That's how this table works, and these show all possible outcomes of rolling two number cubes. Hey, how many possible outcomes are there? Well, there's 6 along this row and 6 in this column. So there's 6 times 6 different possibilities. When I roll two number cubes, there are 36 different outcomes of ones, twos, threes, four. I roll one number on one dice, one on the other. There are 36 possible outcomes. And notice that those outcomes, though, many times, even though like this one's a 2 and a 5 to make a 7, there's many different ways to make a 7. So I get the same number by rolling different numbers added together on each number cube. Okay, now let's think about this. Are there mutually exclusive events tied to a number cube? Well, sure there is. Rolling a 6 and rolling an 8. There's no possible way for me to roll a 6 when I add together both number cubes and an 8 when I add together both number cubes on the same roll, right? It's either going to be a 6 or an 8. So we would say that those are mutually exclusive events. When you flip a coin, you get heads or tails, right? You're either going to get heads or you're going to get tails. You're not going to get both on the same flip. So getting heads, getting tails are mutually exclusive events. To find the probabilities of mutually exclusive events, like let's say we want to know the probability of rolling a 3 or rolling an 11, I just take the probability of the first one, 2 out of 36, plus the probability of the second one, 2 out of 36. I just add them together, and that's the probability of one of those mutually exclusive events being the outcome. So there's a total of 4 possible success outcomes if I'm rolling a 3 or an 11, 4 out of 36. The probability of inclusive events is a little more complicated. Inclusive events can occur at the same time. So this would be like rolling a 6 or rolling an even number. Now, there's there are 5 sixes in this table. So 5 out of 36 outcomes are 6. There's way more even numbers in this table than just the sixes, though. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 different possibilities are even numbers. So rolling a 6 and rolling an even number, think about it, is 6. 6 is an even number. So they're not mutually exclusive because I could roll a 6 that's both an even number and a 6. So inclusive events can occur together on the same trial of an experiment. I roll a 6 and an even number. To deal with that, here's what we need to do. We add the probability of A, probability of a 6, 5 out of 36, and the probability of B, the probability of an even number, that's 18 out of 36. But then I have to subtract out the probability of A and B happening at the same time. So I have to subtract out all sixes that are even numbers. And that's because I double counted the sixes. I counted them once when I counted the probability of a 6. I counted them again when I counted the even numbers. But really, it's the same success, regardless of whether it's a 6 or an even number. So because it's a successful event, I need to subtract the probability of them happening together. All right, let's take a look at how these problems work. Letter A, what is the probability of rolling either a sum of 2 or a sum of 10? I can't roll both a sum of 2 and a sum of 10 at the same time. So letter A is going to be, 1 out of 36 There's only one possible 2 out of all 36 outcomes, plus a sum of 10. Well, there's 3 over 36 tens, 10, 10, 10, okay? I add those together, I get 4 out of 36, which is a probability of 1/9. That's the probability of rolling either a 2 or a 10. This next one's a little bit harder because this is an inclusive event, and inclusive events are always a little bit harder. But we can make inclusive events as easy as possible by making sure we're just counting probabilities. All right, so let's figure this one out. What is the probability of rolling at least one even number or a sum of 3 when using 2 number cubes? Okay, so at least one even number. Let's do that one first. Now, if I roll a 2, I'm rolling one even number. How many numbers are there that I can make if I roll a 2? 6, a 4, 6, a 6, 6. That's a total of 18 different possibilities with a 2, 4, or 6. But that's not all. That's just one number cube. What if I roll a 2 on the other number cube? Now, I already accounted for this 4 in the first 6, but I didn't account for this 3, this 5, or this 7 when I roll a 2 here. So I'm going to count those ones. So we have 18, 19, 20, 21, 22 if I roll a 4, 23, 24, 25, 26, 27. There's a total of 27, and I think I was hovering over the wrong ones here, but there's a total number of 27 different possible outcomes of at least one even number. Okay, that's 27 out of 36 of at least one even number. Now I have to add to that, okay, at least one even number or a 3. Well, let's see. If I roll a 3, there's 2 ways for me to get a 3, a 2 and a 1 or a 1 and a 2. So I'm going to add to that 2 out of 36. But now let's think about this for a second. Did I roll at least one even number to get these 3s? Yes. And actually, I already counted this 3 when I counted the 2 column, and I counted this 3 when I counted across this way. So the way that this is going to work out is I need to subtract the number that is both one even number and a 3. Well, both of my 3s have one even number, so I actually already counted them in the even numbers. So I'm going to subtract both. I'm going to subtract 236 because I have to subtract the probability of A and B happening together. These are both 3s, and they have one even number. Both of them have one even number. Right, so this is just going to be 27 out of 36 when I run it through this equation. Let's make sure that I did that right. Bam, there it is. That can be simplified, by the way. For some reason, I didn't even think about that, but it's if I can put 9 into 27 3 times, 9 into 36 4 times, so 3/4. Letter C. A digital music player randomly selects a song from a group of 12 rock, 12 pop, 5 country, and 3 alternative. 12 plus 12 is 24, plus 8 is 32 different options. Okay, what is the probability that the music player selects either a rock or an alternative song? Well, in this case, rock and alternative are 2 separate categories, so there's no overlap. It's going to be either rock or alternative. No overlap. They're mutually exclusive. So this is the easy kind of problem. It's going to be 12 over, and let me just double check it. 24 plus 8 is 32. 12 over 32, that's the number of rock songs, plus 3 over 32, that's the number of alternative songs. That's going to be a total of 15 over 32. Let's see if that's right. Yes, 15 over 32 is the correct answer. All right, now this one is the big cheese of all of these problems, the hardest one to work, and we really need to think about this one. But you're going to have to be able to work problems like this, so buckle up. We have to figure this one out. Angelina uses Bryson's data from example 3, okay? She's using this information here, in other words. If you want to go back to the book, you can look at lesson 68, example 3. She is planning to call 200 people from Wyoming. She assumes that 10,000 of the people who are 75 and older, that's 10,000 of this group are also employed. Okay, now let's just look at what our data shows here. Bryson has a total population of 510,000. If she's going to call somebody at random, what are the probability that she's going to find somebody who's employed? Well, it's going to be 291,000 over 510,000. It's going to be that proportion. And or I'm sorry, that probability. And then if she what's the probability she's going to call somebody 75 and older? It's going to be 29,000 over 510,000. Are they mutually exclusive groups? Are there any employed people that are also 75 and older? Yes, there's 10,000 people about. That's what she's assuming. So the question is, how many people would Angelina expect to call that are either employed or 75 or older? We're going to see at the end of this. This one's a little different than the other ones that we worked anyway. But the first thing we need to do is figure out a probability. And we're going to use our probability of inclusive events because these are not mutually exclusive, they're inclusive. So it's going to be 291,000 over 510,000. Whoa, whoa, whoa. All these extra zeros. I could just get rid of the zeros and say this is 291 over 510. Okay? And I'm going to add to that the people. Let's see. So, what is the odds that she's going to get, or I'm sorry, probability she's going to get either somebody employed or 75 or older? I need to add this probability 29,000 over 510. Okay, and then I need to subtract the number that are both. The probability of A and B. 10,000 people are both. So I double counted those people. I need to subtract them. It's going to be 10 over 510. All right, so what's my probability? Okay, so let's do the math here. 291 over 510 plus 29 over 510 is going to be 320 over 510. 320 minus 10 over 510 is going to be 310 over 510. And I can simplify this fraction by simply getting rid of this trailing zero because I just divide the numerator and denominator by 10. The probability that I'm going to get somebody who is either employed or 75 and older is 31 over 51. And keep in mind, I already subtracted out the double counted people. So, yes, some of the people will be both, but I only counted the people that are both employed and 75 and older one time. I didn't count them twice. So, this is the actual probability. Now, the question asks, how many people does she expect to call? This is just a probability that any one person is going to be either employed or 75 and older. But now keep in mind, she's calling 200 people. So how do I use that number 200 to get the answer? What if I multiply 200 times the probability of them being employed or 75 and older? Well, when I multiply this is going to tell me how many of those 200 people, what fraction of them do we expect to be both? So let's go ahead and do that. It's going to be 200 times 31 over 51. 121.5. I can't have 0.5 of a person, so I'm just going to round up to 122 people. Let's see if that is correct. There we go. About 122 people are going to be either employed or 75 or older. Some of them will be both. In fact, one out of every 51 of those people, right? 151, 1 over 51, one out of 51 of those people are probably going to be both. So I probably expect there to be 2 or 3 people who are both 75 and older and employed in this group. All right, that is how you work these problems. Now you know what mutually exclusive events are, events that can't possibly occur together. The probabilities of those are the easiest to calculate because you just add the probability of one and the probability of the other to figure out if either or will occur. Inclusive events are a little harder because you double count. If two things can happen together and you count the probability of one of them and the probability of the other, you double counted some of them. So you need to subtract out the double count, the probability of A and B happening at the same time. And now you know how to do that. So for next time, you can work the problem set in lesson 68.